All right, well, welcome everyone. Um, Apologies for my voice. I have a minor case of COVID right now, and it's not really done much to me except for make my voice sound like this, which is fine. But all right, so today we welcome Dr. Russell Stoneback. Dr. Stoneback earned his physics BS at the University of Texas at Austin and his PhD at the University of Texas at Dallas. And while at Dallas, he worked on ion velocity meter, IVM team on CNOF's ICON and the Cosmic 2 satellite missions, including the development of the IVM processing software for ICON and Cosmic 2. He also developed a CubeSat IVM for the Sortie and Sport CubeSats and earned one of his US patents for a neutral wind instrument that will first launch as part of NASA Cousins. Recently, Dr. Stoneback has shifted focus from professorship in satellite instrumentation to science and art by founding his own company, Stoneris, in late 2021. And today he'll give a version of a really nice talk he gave at CEDAR about science and arts. And I promise I didn't invite him just because it involves some guitar stuff, although that certainly helps. And so, as usual, we'll give Dr. Russell first 45 minutes or so, and then, but please put questions in the chat as you have them. So with that, take it away, Russell.
All right, thank you very much for the introduction. So I'm Russell Stoneback, and I'm with Stoneris, and I'm going to be talking about science as art today. And science and art can sometimes be considered very different things. They do have different goals. And while science is typically considered a technical field, which it certainly is, it is also creative. Science in and of itself is a series of discrete experimental measurements. And then on top of those measurements, we've woven a narrative that connects those measurements into a cohesive whole. And while it is a story, it's not arbitrary, right? It has to be something that's consistent with the measurements. But what we've seen more than once in science is that there's more than one story that goes along with explanations of the universe. Art is generally recognized as a very creative process, and it is, but it's also very technical. So depending on the medium, there's all kinds of different choices that an artist has to deal with and confront and problems to be solved to actually express the art in the way that they want. And just over my career, I found I've started some problems with art motivations and ended up with science, and I've started some problems with scientific motivations and ended up with art. So I'm going to just show some of these topics that I've worked on throughout the years that emphasize how science and art can actually be an integrative process. All right, so I'm going to start here with the light guitar. So the light guitar here is a resonant electromagnetic cavity. So the point is to make a new type of musical instrument. And it's going to make music, but it doesn't make sound waves. So it works with a different physical field than acoustic waves. It works with electromagnetic waves. Now there are some particular differences between those two fields. But electromagnetic waves and acoustic waves both satisfy the wave equation. And actually, they have the same boundary conditions as well. So if you have the same differential equations and you have the same boundary conditions, you get the same solutions. So what I'm doing here is I'm building instruments that are the same size as like an acoustic musical instrument, and I'm getting resonances with waves at the same size as an acoustic wave, but with an electromagnetic wave. So that means, right, because light waves are of course much faster than sound waves, the frequency range that these resonances occur is much different. So for an acoustic instrument or human hearing is about 20 hertz to 20 kilohertz. The equivalent range for an electromagnetic musical instrument is about 20 megahertz to 20 gigahertz, and that's because light is about 1 million times faster than sound. So the waveforms that are produced are music, but we can't actually hear them. So in that sense, it's not very good. But with technology, what we can do is we can produce those waves at the native frequencies and wavelengths appropriate, and then use computers and software and things like that to translate those direct measurements into things that we can actually listen to and appreciate the musical qualities. So the way it works is you build a guitar that's made out of metal instead of wood. And then to play it, you measure it with a vector network analyzer, which sends waves down that coax cable right here. Some of the waves go into the guitar based on the impedance difference between the cable and the guitar, and then the rest are reflected back down the cable, and then they're measured by this vector network analyzer. And then I can take those measurements as part of software and recreate the audio effect of the guitar. So it would actually call it an electric guitar because the actual resonant surface is high frequency electrons. It is literally electricity, but the name electric guitar has already been taken. Incidentally, the actual, the standard electric guitar actually records the movement of a string with magnetic fields. So it would officially might be more accurate to call that a magnetic guitar, but here we are. So I've taken the name light guitar because it is electromagnetic waves. It's the same thing as visible waves, which I'm sure everybody on the call knows, but of course just a very different frequency spectrum. So it was actually well established, this relationship between E&M and acoustic fields, and it seemed to have been lost. I found papers in the 50s that started out with an introduction and said, oh, you can just take electromagnetic measurements of something and apply it to acoustic fields, just have the number of modes by 2. And that was the full sentence. So it was well accepted for a while, and then I think it just kind of perhaps gotten lost. But I'm resurrecting it in some way. So for my physics dissertation, I was working on this light guitar. The association, the wave nature of both fields is well established. So what I actually did for physics-wise is solve the diffraction of an aperture. So going back to the guitar, there's actually 2 sets of physics going on here. You have resonant waveguide modes, but then there's also what's called a Helmholtz resonance, and that's an interaction between this opening in the guitar, the aperture or a sound hole, and the cavity itself. So the cavity for acoustic guitar is like a capacitor, and the aperture is like an inductor. Those two produce a resonance. And it's at a wavelength that's much larger than the size of the body itself. So if you blow over a small glass Coke bottle or wine bottle or something like that, you get a really deep note. That's the Helmholtz resonance. Okay. So what I was looking for is to establish that the impedance of an aperture is actually inductive. And I was able to do that. I came up with an impedance description of aperture diffraction, and I also really extended the story of diffraction. So the diffraction story that I started with was generated by beta. It's at long wavelengths. If you try to send a wave through a small hole and a plane conductor, then what happens is it produces a dipole, and that dipole radiates into both spaces, and that's the diffracted field. And that description works well at long wavelengths, but then it really breaks down at shorter wavelengths, and power actually goes to infinity per the method, which is not consistent with reality. So I started with that dipole description at long wavelengths, and then I put it into a system that allowed it to actually function correctly at all wavelengths. So now actually the radiated power as the wavelength goes down to 0 also goes to 0. Some of those are details, but the previous story was that a wave would go, and based on its incident wavelength to the aperture, it would have a particular diffraction response. Turns out that's not actually true. It depends on the radiated wave. So that's a very fundamental shift to the story right there. Hans Bethes' story also had a dipole on both sides. What I found is more consistent is you get a real dipole on the transmitted side, which produces an image field on that side, travels back through the aperture to the other side, producing another image, but an image of an image is real. So the backward transmitted field actually is only kind of a temporary situation. At long wavelengths it exists, but as wavelengths get too smaller compared to the transmitted size, where the transmitted wavelength is small compared to the aperture, then that backwards field goes away. And during that transition, it actually contributes to the forward field, and it can actually produce a superluminal aperture, where that is the diffracted field has more power than is directly incident on the aperture itself. And what's happening is that the currents around the aperture are coupling into that forward radiation. So for a particular wavelength range, you actually get a brighter aperture than you might basically expect. So all of this kind of story came from my description of the aperture in terms of impedance. So I've drawn it here as a circuit. So at longest wavelengths, it's kind of like an inductor. At shorter wavelengths, it's like a capacitor. And then the actual impedances are here. The calculation is actually an admittance. So to get the impedance, I have to take the inverse. All right, probably going too slow. So I take this thing. So I've got a simple description of the aperture, which turns out to be quite accurate and easy to work with. So there was a comparison done by a researcher over in France that had a full wave model thing and launched waves in a waveguide. At the end, there would be an aperture, and it calculated the fields that were radiated out of the aperture. The presented model is me, and then the comparisons is with the CST, which is this fancy wave thing. And you can see the blue curves and the other ones match pretty well. The worst is actually on a circular, but if you go to an elliptical aperture, me and the wave model are pretty much neck and neck. Similarly, if you even move the elliptical aperture off from the center to the side, my model does an extremely good job. And if you have a bunch of apertures all working, my model also does a really good job compared to the full wave solution. So I was able to take a very complicated physical description, diffraction, and reduce it down to an actual accurate solution, overall wavelengths in terms of impedances. So that's pretty significant. So now that I have the impedance of an aperture, I can do things like compare it more to an acoustic guitar. So on this lower level here, an acoustic guitar, measurements were made in the late 70s. So what they're doing in this thing is they've got the guitar and then they cover up the sound hole. So now we no longer get that long wavelength Helmholtz resonance. We just get the body resonances, and it gets a resonance around 163 hertz. They open up the sound hole again, and then you can see we get this Helmholtz thing, which is around 90 hertz, and it modifies the body resonance a little bit. Here's my light guitar on the top left. So with no aperture, we get a body resonance thing around 150, 160 megahertz. So, take a million off. That's the same frequency, the same wavelength. And then if I take my aperture impedance and I couple it with the measured light guitar capacitive impedance, then we get this Helmholtz resonance at 100 megahertz, or that's about 100 hertz or so, which is exactly the right type of thing. So we're getting the same type of responses in the light guitar as we are getting out of the acoustic guitar, which kind of validates my dissertation work, which is great. So one of the reasons to do a light guitar is I've tried to motivate that the light guitar works like an acoustic guitar based on the physical equations, but an acoustic guitar is not, the point isn't to make the exact same thing. So one, electromagnetic fields are more complicated. There's twice as many modes. So for a light guitar, you're actually going to have more modes going on. So, and different polarization and things like that. So if you're going to measure the response outside the guitar with, say, an antenna, you have different ways to couple that provides variations that musicians would be interested in. Further, an acoustic guitar has a response that's actually pretty limited because there's all kinds of bracing and stuff inside the guitar. The reason being that the strings attached to the guitar are under tension, and if the guitar wasn't rigid, then the thing would collapse upon itself. However, if it's super rigid, then it doesn't radiate sound at all. So there's a definite balance in acoustic guitar between the top plate being mobile enough to be responsive to the sounds played, while being strong enough to actually withstand, being around for a while. So that really limits the high frequency response to the acoustic guitar. Typically above around a kilohertz or so, the acoustic guitar is done. But for the light guitar, there's no bracing, right? Well, one, there's no strings attached to its tension, but the structure that holds it together is just some plastic stuff, and it's on the outside. So the plastic is basically transparent to all these ways. It just doesn't care. So it doesn't interfere with any of those higher wavelength or higher frequency behavior. So you can see here on the blue for the light guitar that as you move into higher frequencies, there's just a lot of wave structure, a lot of resonant structure in here. So that's provides interest for musicians. All right, so how do we actually hear this? So I wrote a plugin to run in Apple's GarageBand or Logic software. This was written over 10 years ago, so it's actually aged out. But what I do is I take measurements of the light guitar here. So it's a frequency response curve, and then I can convert that to an impulse, right? So if I take that impulse and I convolve it with input music, then it's like the music was played through the light guitar. So this technique is commonly used for like reverb. So if you want to, make it sound like you're in my office here, then what I can do is I can measure the impulse of this office. And then if I convolve that then in your recordings, it's going to sound like it's in here. Or if you want to do, not my office, some famous place, some famous opera house or something like that, you take like a starter pistol or something there. When you fire that off, that provides a sharp impulse. And then if you record that with a microphone, that impulse, it records everything about the space. Every little bit about the response to that room is encoded in that measured impulse. So it's basically like a reverb type plugin, but it's a much shorter time frame. So there's technical challenges. But you send music in one side, you convolve it with the measurements, and on the output, you get music with the same type of response if it went through the light guitar at higher frequencies. So here's the light. If there are any questions, I don't see the chat, so please, somebody's going to have to speak up for me.
I will do that.
All right. All right, so that was the artistic motivation. So I wanted to make a light guitar, and I did the physics to make that happen. And I was hoping to do a demo. I got all the stuff here, but technical reasons I couldn't get the mics and teams to work, so unfortunately that's not going to happen. What was surprising was while I was doing this, worked for making music, I actually found a direct space science connection. So while I was looking up aperture behaviors, I found this paper that was also done in France. So what they did here is they've got a silver layer, and they made a very small aperture, a couple hundred nanometers in diameter, and then they sent high frequency electrons through it, or they sent plasma through it. And when they send the plasma through it, the aperture glows because it's diffracting through just like if it was an electromagnetic wave. The reason they're using plasma, though, is because on the opposite side, they got some kind of light detector, and if they sent light in, some of that stray light could mess with the measurement. So if they send electrons in, and then they just measure the glow from the electrons, then they get a more refined measurement of just what the glow from the aperture is. So this is the glow from the aperture as this plasma is going through. The blue is the experimental data. The red is my theoretical model, which does a really great job. It's really designed only for long wavelengths, so things like way back over here. But even so, I do a good job even when the wavelengths get shorter, because I have a definitely an improved model of dipole diffraction. And then this glow here, when I did a full wave model, full finite element model, wave analysis of an aperture and a conductor using ANSYS, find you get these really kind of intense fields just outside the aperture. And it's these normal to the aperture plane. So it's these intense electric fields that are the things that generate the glow. And then, of course, there's an electric field right across. So the connection to space science actually is the Earth itself. So I like to say the Earth is a light guitar. So the guitar itself is a cavity with an aperture. So the Earth cavities, you got the ionosphere and you got the Earth that forms a resonant cavity. We already know that because we have the Schumann resonances around about 7 to 8 hertz, right? And at the polar, claim is that is an aperture. It's a physical claim, right? An aperture is an area of low horizontal conductivity surrounded by an area of high horizontal conductivity. Well, the polar ionosphere, the magnetic fields are basically straight up and down, and the direct conductivity along the field line is the biggest. So side to side, all you have is the Hall-Peterson conductivities, which are not very big compared to the direct. Once you get out of the polar cap, you get a little inclination to the magnetic field, and now you have a horizontal conductivity component from the direct that is much larger than anywhere. So everywhere outside this glowy region, right, higher horizontal conductivity. Inside the aurora here, low horizontal conductivity. Now I'm showing a picture of aurora because it's just a nice visual demonstration of the boundary conditions that I'm relying on, right? So you got closed field lines, equatorward of the polar ionosphere, and then the poles, that's the aperture. So if we're talking about like as the solar wind flows past the Earth, the transfer of power between the solar wind and the Earth is going to be mediated by the impedance of this aperture, or the coupling of the aperture with the Earth. So I've built a model based on the Earth being a light guitar using the same physics I was just talking about. So here's a description of the Birkeland currents distribution, right? You got currents coming down on one side, flows across the polar ionosphere, coming back up, the region 1s. And then you've got closure currents region 2 that are on the closed field lines, right? So you tend to get distributions that look like this. This is Birkeland current observations. It's seeded with measurements and then a simulation that went on. And you can see, right, you've got an up, down, down, up type distribution. Same here. Well, this is a slice from my ANSYS model of an aperture. This is the normal electric field distribution. So you've got the same thing down, up, down, right? You have the same normal electric field in an aperture as you do in the polar ionosphere. And when I first saw this, I almost fell out of my computer chair because I was like, what does this? Well, actually, when I saw the Birkeland currents, I was taking intro space science class. I was like, what are the Birkeland currents? What is aperture fields having to do with the polar ionosphere? The only way you get the same electric fields is if you have the same boundary conditions. And then it turns out, right, we do have the same boundary conditions. So here's my model. It's not to scale, of course, but this is the ionosphere. I'm just, it's a conductor. Here's the Earth. It's also conductive. You got the oceans. You got all kinds of metals and other things in the ground. So the Earth is conductive enough. Again, the Schumann resonances, and then the polar ionosphere, if often waves come down here when they hit this aperture, some of them are going to transmit based on the difference in the local impedance to this cavity impedance, and then the rest reflect off. And then so my predictions are here in blue, and then measurements actually done by a fast spacecraft published here are in black. I just copied them out of the paper. A normal aperture, you have an electric and magnetic dipole, and those two things are coupled together. You don't the impedance is the same, like you get one overall impedance. But with the Earth, you've got the aperture, and then you've got the Earth, which is like really super close. It's actually much closer than even the size of the aperture. So it messes with the normal impedances. So it actually breaks the degeneracy between these two modes, and you actually get one where the electric dipole is acting the magnetic dipole in this aperture description. So I forget which one. I think the dark here is the electric dipole, and then the dashed here is the magnetic dipole coupling. So this is during a substorm, so there's all kinds of currents and stuff rushing towards the polar cap. Now it's a conductive area, but all currents going down like that's equivalent to a normal electric field. So this is the transmitted power based on electric dipole coupling, and it matches very well. There's also the magnetic one, which is not displayed as much, but again, I think in this case, because it's a storm, all the power is in the normal electric field. Measurements here that they also did of the alpha and wave velocity by the spacecraft shows something interesting, because the blue curve and the black dots match pretty well here. They don't match well down here. The thing is, the deflection transmission of power is determined by this impedance mismatch, and alpha and wave velocity is actually just a reformulation of impedance. So these two curves the black curves should match, and the relationship doesn't match. So this is not consistent with like a single thing going on. There's more than one impedance thing going on in the polar atmosphere measurements from the satellite measurements. The thing is, the velocity measurements do match what the magnetic dipole is doing very well. So that's nice. The reason I think that you see electric dipole in one and magnetic dipole in the other is, well, the boundary conditions actually prevents any power transmitted in the electric field, electric dipole being radiated away. So you're not actually going to see it in the waves that this thing is measuring, but you would measure the lack of power. On the other hand, the magnetic dipole doesn't have that kind of restriction on the transmitted power, so you would be able to see it in waves. So I think that's why it matches down here on the waves, the measured wave speed very well. There's also been some lower frequency oscillations measured around the globe, and I actually get the same frequencies for power instead of going from space to Earth, but from Earth to space. As I said before, the diffraction through an aperture depends on the region, the materials it's radiating into. So that's where this is coming from. And then the magnetic and electric give a slight difference in the actual frequencies, and so that would lead to a beat frequency here, which is actually consistent with structured oscillations. And then the distribution of the closed and open field lines versus the boundary conditions would mean that the structured oscillations would be what part, but this unstructured would be equatorward, which is also consistent with some observations. So the way I'm generating all these things, I'm just using the impedances that I've calculated. So I have an alpha and wave impedance, which alpha and wave impedance, and then the polar here, this is my polar aperture combined with an alpha and wave. So this is just a standard network relation. If you've got two, medium 1, medium 2, and waves are coming here, transmitted power and reflected power, all that, this is just this standard boundary condition. So all this is boundary conditions. So it works really well for the Earth. So I said, well, the Earth and the Sun basically have the same kind of magnetic structure. Well, what about the Sun? Solar scientists are already calling the polar regions a coronal hole, though they're calling it a hole because it looks like one. The current explanation, right, is the fields are open, so it allows the plasma to stream out. So that allows for a difference, and the visual how it looks. I'm doing the same thing here. When I actually looked up, review papers on the Sun, and incidentally, I actually spent more of the summer studying the Sun. But the chromosphere is very similar in ways to the Earth's ionosphere. And one of the review papers I read said the chromosphere is just like the Earth's ionosphere. Exactly. So it's neutral, partially ionized, all that stuff. So what I did is I put a polar aperture in it for the Sun, and then I calculated what's the transmission power of waves going from the chromosphere to the corona. That has been a long-standing problem in solar physics because there's an impedance difference between those two regions, which would normally reflect all those waves that are trying to cross that boundary, which would prevent the transfer of power. In my case, I add the impedance of the aperture to the coronal hole, and the combined impedance of the chromosphere plus the aperture matches the corona around a 5-minute period. consistent with observations. So here's my model of the transfer of power from chromosphere to corona using average properties of the chromosphere and corona and coronal hole size, all that stuff. Yeah, and then I compared it to some helioseismology measurements that are just on the web. Of course, the helioseismology is all about the oscillations of the sun. And here I'm looking at the transfer of alpha wave power, but those things just really line up right on top of each other. So I just took my plot, right, and just lined up the frequencies. So it actually works well for the Earth. It works well for the sun. Same model for the sunspot. I do the same thing. This is results from a particular size sunspot, but I can calculate transmitted power from the sunspot out, and I find that you get a maximum transmitted power at around a 3-minute period. This is from the Umbra, which is consistent with observations. I didn't include this one slide, but I calculated this one assuming in the Umbra fields are more vertical, right? So when waves are going out, they're going to experience like the coronal environment. So I put in the coronal environment here for the transmitted, the second region. The region is going to be radiated into, gives me a 3-minute period. If I put in the chromosphere instead for the, the region that it radiates into, I get like a 7-minute. Oh, I should include the slide. Crap. It increases the period consistent with what's actually found in the penumbra. And in the penumbra, right, the fields are not so vertical. So I actually think that sunspots are literal electromagnetic apertures, and the impedance of that aperture is what converts the acoustic wave energy on one side into alpha waves, which allows the radiation and then the reduction in temperature. So I built a simple model. I assumed I had a wave that's going in the photosphere to the chromosphere boundary. Any power that's radiated back is assumed to be perfectly absorbed and converted into temperature. So I can then figure out if I reduce that some, then I can calculate what the impact upon temperature is. And just by doing this, you put in the reflected power peak like this, and then you can actually calculate the right temperatures for the umbra and the penumbra based on the photosphere temperature. So I'm finding my diffraction, my aperture diffraction, and my Earth is a light guitar, Sun is a light guitar works over many orders of magnitude, from something the size of this all the way up to the size of the Sun's coronal hole. Now, some of you, the Earth's magnetic field is much simpler, right, than the Sun's magnetic field. Though, of course, the Sun has got a cycle, but it gets more complicated, and you get all kinds of extra loops and things like that. And you might wonder, well, how do those things actually all go together? Well, I got to refer you back to this thing here. You can have a bunch of apertures, and my method still works. So you could have, the big overall coronal hole is the big aperture, and there might be loops and stuff within that. And so that might be local variations on the behavior, but on a larger scale, you're still going to end up with the same behavior. The impedance of an aperture is overwhelmingly dominated by a dipole. Just orders of magnitude dominated by the dipole response for almost overall wavelengths. So there we go. Okay. So that was a very super fast light guitar, and Earth was a light guitar thing. But my experience in light guitars and my work with music actually turned out to have more space science applications. So in this case, I'm going to be shifting actually into PySat a little bit, which is some open source software I've been working on along with some folks, Jeff Clenzy and Jonathan Smith, and at NASA, and Angeline Burrell at NRL. But one of the problems we're faced with in space science right now is dealing with data. So like the history of space science, there would be a mission, and you'd have a bunch of scientists working on one satellite with one or a few instruments, right? Each instrument's got multiple people working on it. And it takes people, everybody's got to kind of get together and work to get everything working, and it's a real massive team affair. Except at the same time now, companies like SpaceX are literally launching thousands of satellites all the time. So our current, having many scientists per instrument is not going to scale in a world where we actually hopefully can get thousands and thousands of instruments on satellites going right now. And it turned out music and audio recording has already gone through a transition like this. And with my experience with music and recording engineering, is something I've been picking up on. So here's some pictures of like in the 20s to 40s, if you wanted to record a song, you had to get all the musicians into the same room at the same time, and they'd sing into one or two microphones. That were limited by the technology at the time. They could only record one or like 2 tracks. So that's actually, it's not bad to have everybody in the room at the same time. If you take all modern equipment, you get every musician into a room at once, you put one microphone in the middle, that'll produce a very authentic recording. And by authentic, I mean if you were actually there while the musicians were playing it and recording it and you stood next to the microphone, that recording would sound the most like you're actually there. So anyway, so it's not a bad way to go, but it's just a challenging way to go because you have to get everybody together all at once. So here you've only got a few people. But if you want to, piano and instrumentation and other things at the same time, you need a band director, you need all your backup singers, you need the musicians, you need the piano person, you need the bassist, and again, you're still limited to one or two microphones. Wanted somebody in the mix in the overall sound to be louder or softer, they either had to play louder or softer, or you had to move the microphone. And if you got a bunch of people, right, it becomes a challenge. How do you get everybody spaced out in the way that sounds good and all that? And that's why you'd have like the director, or here's even into the 50s. So like the first multi-track recorder was sold to Les Paul in the mid 50s for $10K, and then that started spreading in the studio. So rather than having to get everybody together at once, you could have a musician record something in LA, and then months later somebody else in New York, and then do something else, and then even later have some singers somewhere else do something. Or you could have the main singer sing the main vocals and do the backup vocals and harmonies and other things like that. You don't actually need other singers. So the recording, the engineering flow that kind of worked to make studio recording and albums easier to produce is something that we can directly benefit from in space science. So this console over here is actually the console that Dark Side of the Moon was recorded on. I think this is 1973. That's also the year that I think the SMTP protocol came out. It was a time protocol, which is like the final piece of audio engineering workflow that allows you to have multiple multi-track machines recording and playback all sync together. So now you can have like infinite tracks. And in this console and this hardware, there's a whole workflow of you have a microphone measuring something, and then you can do whatever you want. And they had to actually encode that in hardware to meet the artistic demands of all the musicians, right? So it's engineering directly driven by creative works, and it allowed engineers from the 70s. The workflow by then is complete. So this is the Dark Side of the Moon console. Here's like a current console you can just buy off the internet. It's the same workflow, even though now this is all digital. The workflow that was developed over the years is still in this, and this is a screenshot from Logic, Apple's fancier music recording thing. It's the same workflow, even digital. So what I found in music is that we can use this workflow for data science. So what we need to move to is having a scientist here in the middle, one scientist now, and then this whole orchestra is representative of the thousands of different data sources that one scientist needs to be able to control, and be like, give me more of this, less of this, more of that, less of that, faster, slower, whatever. We need to be able to have tools where one person can scale to many sources. So yeah, that requires a lot of software and other infrastructure. And that's what PySat is. I've taken that, along with the other people on the team, of course, taken that workflow and built it into what we call an instrument object, which is like the main interface for a scientist to any data set. Any data set, independent of dimensionality or source or anything like that. So yeah, and then on top of that, we're building a constellation, which would be an arbitrary grouping of instruments. So then the satellite, sorry, so a scientist then could, work with solar space weather indices or satellite data or remote profile data or ground-based data or model data, all that, be able to, within software, have all that just within one object to work on. And it allows the same versatility, that the recording engineers have with music. So you can pop in and change things and tweak things and all that in a very versatile, but importantly, a very systematic way. So that's all been, built into PySat. I also have I keep talking about music, so I do have a demo recording up on YouTube that you can check out if you want. It's a cover of Seven Nation Army, originally done by the White Stripes. It's posted under Mr. Kiwi. So you search Seven Nation Army, YouTube, Mr. Kiwi, this will come up. So these are basically like the same thing. That's why it's on the same slide. So one's music version, the other's data science version, but it's the same workflows. It's kind of demonstrating my same expertise. So PySat, as I was trying to say, is like this generalized, very easy to use interface to all data in the world. It doesn't matter what the source is, doesn't matter what the file format is, all kinds of stuff like that. But it turns out, if you're getting files from a particular source, say CEDAWeb, a lot of getting the data is the same. So we've collected different sources into their individual packages. So PySat NASA has support for NASA data from CEDAWeb. PySat CDAC has instruments and methods tuned to interacting with data from CDAC, Cosmic Data and Analysis Archive Center. Similarly, PySat Magical is like a plugin that includes methods and data sets from Madrigal, the NSF, Open Madrigal database. So we've got a variety of different data sources that all couple into PySat. So if a user comes along, they just interact with PySat, and then the data comes from these different sources and mostly transparent way. So regardless of what the data is or where it comes from or the form, a scientist gets to work with it just in the same way because it's all encapsulated within easy to use objects. Just kind of like, not just like record and engineer with their very generalized workflows. And then we've got all kinds of analysis and other things. And PySat's been used on Icon and Cosmic. I've used it as a foundation to write the IBM software on top of. It's also coupled with my magnetic basis vectors, and I'm way behind, so I'm going to be moving on. We got a lot of documentation. So PySat's up on GitHub. It's intended to be a community-wide package for even mission processing, all the way from mission processing, file creation for distribution. Icon and Cosmic 2 files were made from PySat, things like that, all the way through scientific analysis. So there's a lot of documentation and other things up online and analysis procedures that are instrument independent, and we're all very documented and coupled, and there we go. So so I'm going to be moving on to now some of the orthogonal vector basis. So this is a direct space science thing. I started on this project way back like 2009 as part of the CNOS project, where I was directed, hey, I need to come up with a vector system that accurately describes ion drifts. And so the challenge is that and a magnetized plasma is really, its behavior is highly driven by the structure of the magnetic field, and magnetic field lines are considered equipotential in plasma. So if you have an electric field, say here, that electric field will map along the magnetic field line by maintaining, right, the potential is going to be the same along this field line everywhere. Of course, the distance between those two changes, so the electric field changes based on the structure of the magnetic field, and then typically they want to be divided into, you want something orthogonal, so normal vector stuff works and physics works, right? So a field-aligned direction that's along the magnetic field. A zonal would be like a magnetic eastward, so it's perpendicular to the field line. And then meridional would also be perpendicular to the field line and the zonal, and generally in the upward direction at the magnetic equator. So I had to come up with a way to actually calculate an orthogonal basis system that works for the Earth's magnetic field, or a multipole magnetic field. Generally, the Earth is largely dipole, but it's not really, right? It's got more complicated components. And then the current, so that matters because the current solutions out there claim that you can't actually have an orthogonal system if the field is more complicated than a dipole, and the planet is more complicated than a sphere. The reason being, with their method, is they take from the surface and project out based on a dipole thing. So if you violate any of those, then the orthogonality no longer works. However, just as a thought argument, you have a magnetic field. Let's assume it's dipole, the planet spherical. You have an orthogonal thing based on the magnetic field. Now I changed the planet, and somehow the orthogonal basis on the magnetic field is supposed to be broken, but the field didn't change at all. The magnetic field is the same field as it always was, so a linear basis still has to be possible. And E&M fields are linear, so if the true claim is that you can't have an actual orthogonal basis in complicated fields, that would be inconsistent with the linear nature of electromagnetic fields. So if the current vectors we have are a challenge even in a field like the Earth, but if we want to do electrodynamics on the sun, fields are even more complicated. Or if we want to do it on Mars, fields are very complicated again because the Mars field is all crustal, so there's not like one overall major dipole component. So we need a system that works for the Earth, the sun, the Mars, and everything in between, right? So I came up with a new vector basis, which I'm going to have to be very quick here, but rather than having like this whole global thing, what it does is it just maps to the magnetic equator, and it finds the vector that at the magnetic equator is horizontal in terms of apex height. And then that defines the zonal vector. And then there's other things you can do, but from that zonal vector and the field of line, you can form a fully complete orthogonal basis. can even go the other way, calculate the meridional and all that. But that's the main thing. So here we go. I don't have time for all the math. So what I did is there's two ways to calculate the basis. One that calculates the zonal and then gets the rest. The other way is you calculate the meridional and then get the rest just from vector things. Those will only be the same if the underlying system actually is correct, if you actually get the right meridional vector from direct calculation or the right zonal vector from direct calculation. So when I compare the normalized difference between these two systems, what I get for a dipole spherical Earth is, it's 10 to the minus 6 or better. If I move to a geodetic Earth, it doesn't change because the Earth shouldn't matter. If I add a quadrupole field, even with a geodetic Earth, then again, it still doesn't matter, doesn't affect the performance. Add a quadrupole, a more complicated quadrupole field. So this is a pair of quadrupoles now in the X. Doesn't matter. I add a pair of normal quadrupoles, and then it's still, the performance doesn't matter. And then I go to IOGRF, and then again, if you look at the top numbers, it doesn't change. So this basis I have works independent of magnetic field, which is really fundamental for space science, because apparently for how many years now we've had satellites been measuring things, and the ground station has been measuring purportedly the same thing. There's been no way to actually directly compare those two measurements together. Or the ICON mission is launched and wants to compare ion drifts with neutral winds, but those are at different places on the field line. You actually need OMMBV, this new basis thing I came up with, to do that science-wise. All right, so that's the science. But while I was doing, there's a whole vast array of different processes in there, and I wanted to make sure everything was accurate. I had to generate unit tests to establish the performance of each subcomponent of the full software, right? And then I was plotting it because I wanted to make sure I didn't have any longitudinal or latitudinal biases, stuff like that. And then as I was plotting these unit test plots where I would just literally calculate some vector quantity or some quantity, and then I calculate the same quantity again with a slightly different, value for one of the parameters, and I take the difference. What was popping out was like artwork. So this is an uncertainty plot from OMMBV. I calculate, one of the properties. This is actual uncertainty in the orthogonality, how correct I am. So this is an accuracy plot. It's actually, and this doesn't look like any kind of unit test plot I've looked at before. It actually looks like, some intentional piece of art that is some painting. The way I painted this was my perspective on physics and trying to build the best possible software that I could. This is just the result that comes out because of, the way I approach software. So this is like at 10 to the minus 7 and better, generally on this orthogonality. So it's high performance. When actually one of the main qualities that goes into is the apex height, and at the equator that's at normalized errors like 10 to the minus 12. So, but it depends on how long you go. Here's another quantity where in this case the geomagnetic equator now is just popping out, right? It's really super bright, and it's still got that same kind of complex kind of painted artwork and shifted paint and all kinds of other things going on. So what I'm using for the color maps here is I'm actually using the perceptually uniform color maps in Matplotlib, where the perceived change of brightness is supposed to map accurately right to the actual change in the data. So this is just actually, popping out how things, a very accurate visual depiction of what the data is doing. And there's all kinds of different structures. Like you get these bands that show up and then kind of disappear, but they're consistent in ways, and complicated, and it's got depth. Gaming things is just like explorations of color. So this is the same process. I only got one piece of code to make all this artwork. I just send in different pieces of data. So this is plotted in the exact same way as the other one is. The other two were just a different color map, and it's just different data. And for whatever reason, the distribution of the data is auto scale. All the other colors are in there somehow, but generally you don't see. You just see this kind of cool green kind of thing coming through with lots of structure. Here's another one that comes out. So it's everything's about field line tracing. So these areas here, these dark lines, these are low uncertainty areas, super low uncertainty. So it kind of reflects that. This is my guess now. If you're at some location, right, this is known. If wherever you're at, when you're calculating this basis, it's mapped to the magnetic equator. So everything's at the magnetic equator. So whatever the properties are there will map along the field line. So if for whatever reason it's very low uncertainty calculation at the magnetic field line, I could see that would map along a field line, which it looks like that's what's happening here. These are the magnetic poles. right? But then it actually happens in some complex way. It's like a bunch of dots, and sometimes they go away, sometimes they come back. It's kind of interesting. But then it raises the question of what's this circle here, right? It's apparently something local, but it's not a local method. So this is low uncertainty, so it's not a problem. But I also don't expect, like, why is this circle here? I really don't know. I can also just look at the more typical uncertainty maps. This is uncertainty, the geodetic transformation that I'm using. But it comes out as a very kind of nice piece of modern art. So again, the colors just come out how they are. In this case, there's a lot of areas where the uncertainty was 0. So when I'm taking a log, so I make sure, to get the full range of errors, log of 0 is not happy. So any of those places here where there's no uncertainty, I just backfilled with white. That's similar with this one. So this is at all latitudes, all longitudes. This is just at the magnetic equator. So this is how things looked when I first was starting on this project. So it's kind of black here and over here. And it just seemed like things were straight up and down, but then you expand to higher latitudes and you get all these emerging circles and other things that kind of pop out, and whatever this stuff is. I don't know, it's pretty interesting though. Here's just another uncertainty plot. So one, because of perceptually uniform colors, the way the color maps are, making sure the changes in data map changes and perceived brightness, it really has, a lot of pop here in the middle. But at the same time, it's not too harsh, but it really, it's brighter, isn't it? And then the colors that are just coming out on the sides are just really cool. And then there's all kinds of structure here in the middle. There's all kinds of complicated stuff going on here. So it's not, some of these pieces are simple, but they have depth, right? I mean, simple top and ways, but there's still a lot of depth and things to go on. So this one, again, is just another uncertainty plot. And whatever's going on here, it seems to fade away, right? All those little dots that are forming those lines, they all kind of I don't know where they're going. And it's just really nice transitions of color and things like that. So I mean, if I didn't know that this is just something that popped out for my physics, I mean, this looks like something that an artist actually did. And I am claiming to be the artist here because it's my physics, my software, my perceived view of how the basis functions would actually come out accurately is being reflected in these things. And it's all at kind of, pretty down, I've already got a number of established significant figures here. So I think if somebody else wrote the software, these plots wouldn't be coming out exactly the same because the certainties wouldn't be the same. Anyway, it's not just colors. You can even have things that, I mean, there are colors here, but it's interesting because there's perceived a lot of gray kind of coming in here in the blue, but it turns out there actually is no gray in these color maps. So it's a combination of, in this case, the areas with no uncertainty are white. And the combination of the different white densities with the blue is actually producing colors that are outside the direct color map. And then here we've got all these kinds of distortion. Distortion is probably Moire lines, which I think is probably coming from me looking at differences over spatial scales that are smaller than IGRF is really defined at. And I believe I was told that there's techniques I can do for this subsampling interpolation to remove some of these things. So that'll be like a future deal. But for the moment now, for art, it's got you get all these kind of lots of interesting details and stuff that are spread throughout the art. That's a zoom in. Here's full latitudes. I didn't know that the magnetic poles were kind of like flowers. Of course, it's a little distorted here because it's a latitude-longitude map, but if I did something that's, say centered at the geographic pole and, circular map, the magnetic poles would be off-center, and it would probably really know that this kind of repeated extended floral thing. And again, I mean, this is an uncertainty plot, and the colors just come out how they are, and this thing is just really surprising. This is actual direct output, so now I'm actually looking at unit vector or I don't, scaling factor or something like that. So again, here's the geomagnetic equator just popping out at you. In this case, had it as the dark color, and then it leaves everything else to be, where all the intensity's at. This is I think this is all the zonal vector different components. I think this might be the eastward component. So this is the Inferno color map, I think, and it actually, it lives up to its name. I mean, down here, that's really bright. It's got that perceived brightness, and there's a certain intensity that the color maps bring to these to make it art. And normally, I don't really like a lot of oranges, but these things are coming out with some, I think, interesting oranges and purples and pinks and all kinds of colors. I actually have more than 5,000 of these images. I'm not actually even done. Uh, So, I'm just kind of getting started with some of this magnetic basis thing, but, the artwork that comes out of it is just really quite remarkable. And I'm quite proud because it's also a significant advancement in space science now, right? You can actually compare ground stations to satellites for models actually want to physically generate, ionosphere. They don't have to model everything along the field line now. You can just do everything at the magnetic equator, run everything there, and then when you're done, you can just use my basis vectors to map that thing, map those results everywhere along those field lines accurately. Maintain all the properties of the vectors everywhere. So if you remove a dimension from a physical model, I mean, the speed up or the amount of resolution increase that you can have, I mean, I'd say have fun. So I know I'm running a little over, I think, but I only have a few slides left, and I'm going to go through these fast. So I've been working with the Python and Heliophysics group, right, for my PySat and the other software as part of the PySat development team. We've got a whole ecosystem that we're working on, where pretty much everything in space science is possible. I mean, everything that you need to do in space science is possible through PySat, or coupling to other packages in the system via PySat. But I've been working with the Python and Heliophysics group for a while, and mostly, as a consequence of funding and just the way science is. I mean, we meet up for meetings, but most of the time people are doing their own thing. There are efforts to get stuff going around, but there hasn't been, sufficient funding for that. So recently we had our first summer school as part of this group, and some of us went out to Spain, to Madrid, to the ESAC, an ESA center. And had a summer school packages, and the development of that conference and the summer school, right, required a number of the packages to all get together. We all had to work to a common goal, which was get all our software working on HelioCloud and produce a bunch of good content and make sure everything works out well. And it went fantastically. So after the conference, I was like, well, that was great. Let's see if we can keep using that kind of things to advance open source science software by having some kind of focus for the PyHC community to work on. So we've been talking about having a conference, perhaps even in Plano, where I'm at here in Plano, in 2024 to go along with the eclipse. And a good conference center, which is just behind the center, has a pond out back. I mean, pond is pretty good size. And it could be just the perfect place to put a little mini solar observatory, like a CubeSat observatory, not for people, just big enough for equipment. And then, run power and cables and internet connectivity and all that through the lake up to that conference center. Then the thing is, the community, we could, I'm sorry, I'm getting ahead of myself on this whole thing. So that's the setup. So we want a CubeSat solar observatory. It can put it in a place where we're going to already going to have scientists and then celebrate the total eclipse by having it ready by there. And then it's conveniently located for a lot of people in the country to come and visit if they wanted to, in an area that is much easier to get to. So the idea is that we're going to focus on the data flow from the solar observatory as part of the thing. So if we actually have an instrument, then groups like SunPy, PySat, Komodo is doing visualizations. We could all get together and build a workflow to process all the solar data in good ways. PySat can help connect all the pieces. SunPy's already got all the solar stuff, right? Komodo's already focused on visualization. So we build a nice data flow to visualize it. And then if to spread it to other people, we could even work with the happy people at NASA. Right now, NASA's configured to go from like server to out. In principle, it could be modified to go from all those outward people back in. So it could be a way for like citizen science type things to dump all their data in a way that's connected to the normal scientists and professional space science, right? So the idea being is use the conference and all that to couple all of our packages together by actually having a specific data flow to work on. If we have, an actual target, it makes things much easier to work on. But on top of that, we're having a problem in this country and around the world of connecting to people with science. Science can figure out things about the world and as not getting translated to other people. Things like pandemic, climate change, all kinds of things like that really have significant impacts for our future. So with this coupling of the art, it offers science as art. It offers a way to do outreach that doesn't actually require like, oh, hey, I'm a scientist and I'm going to show you some plots and I'm going to teach you stuff and here's time for a lecture and all kinds of stuff like that. No, you just use the science to generate art, so it can just be a way for people to enjoy it, right? It doesn't require a lecture, it doesn't require math, it doesn't require all kinds of study, and they can like it or they can not. But it's something that's low requirements, right? But it gives them a way to actually connect to the universe in ways that they may not have before. I forgot to actually get these slides. I can't believe I did that, but. Right, the new infrared telescope went up, and people on Twitter, has been all over Twitter, right? And when it was first coming out, and it had the pictures, all the galaxies distorted and stuff, somebody actually overlaid that on top of Starry Night. Yeah, Starry Night, where it had all the swirls and stuff like that. I believe it was Starry Night, and it actually worked out pretty well. So there's already people out there that want to view the universe in artistic type of ways, but kind of the normal paths of funding and stuff in the government with everything in a box and all that, cuts all that stuff off. Another example, now this is, it's Hollywood, but in the movie Contact, when that astronaut, Jodie Foster, actually went off to the other place and was seeing everything and was so moved by it, her response was like, they should have sent a poet, right? Because poets, you might be able to take pictures and stuff and show what it actually looks like, but when a poet describes something, it allows people that weren't there to experience what it feels like. So I'm trying to use some of the science and art stuff to actually just give people an emotional connection, just produce some feeling, allow them to look at the sun in a different way. So that's all a long-winded way to say we need to brand the sun. By branding, I mean like corporate type branding, advertising branding. I mean, corporations have figured out advertising and branding is the way to go, probably ever since the pet rock. And as scientists, we just kept going on doing our scientist thing, right? And we're like, science, science, science. But we're missing out on some of this branding. Now, I'm seeing it on Twitter and people are coming into it in their own ways, but it'd be really good if we actually had more official, pushes towards that. So one thing we could do is I could, as part of the conference, OMMBV could couple into the solar fields to actually generate a whole new series, a physics understanding of the sun. Can we actually my technique, I think, will work for the sun and generate a complete map of the electrodynamics on the sun, so you can translate a measurement from anywhere else. Set up that whole open source process, so that's the thing that could just be done as a normal everyday thing, so scientists could actually understand, that type of thing. And then we would reveal that information as part of the conference, not only just in science form, but in like artwork form. Like I do this same stuff again. I generate unit test plots for the solar field, and solar art would come out, right? And it's going to be different. I don't know how, but it's going to be different. On top, we can also set up things so that if people are at the conference center, because this conference center has like weddings and corporate events and graduations and birthdays and whatever, if you want to couple some of the outputs of that mini solar observatory to that event, allow a personal, emotional connection. And usually that's with color. So one way you could do that is you could have like a card or a placard or something that goes on each table, label "Our love is brighter than the sun." Right, and then on one side you'd start with the bride color, on the other side you'd have the groom color, and then when you switch from those over into those perceptually uniform color maps, so then when you get into the center, it's really bright again. So you actually get like that perceived thing. You can also have like corporate events, Q4 profits are stellar. Graduations, my future is so bright, right? And then you can even put the shades on the sun. Right? Maybe a little cheesy or whatever, but you want people to have things that aren't cheesy or sappy or emotional or fun or whatever. Just so you could get away with, say, a single telescope with a multi wavelength filter. You take pictures separated by time, and then they'll give you a variety of images. You can, if you have 3 different wavelengths, you can assign that RGB, so then you can get to the bride color or the groom color. And then from there, when you move to the middle, you'd have to switch to something else, like a color map. So there'd be some work to do. And if there are any solar scientists on the call, I'm sure you're going, I put the brightest spot here in the middle, but that's not actually how the pictures look, right? Because you're going through the least distance through the corona there. But if you just reverse the color map, so perhaps the darker areas are brighter, then it pops out. I know, like I've complained so many times with movies and other things when they distort science, but sometimes, right, this is about an emotional connection, not strictly a scientist one. But if you get somebody interested in the sun in a real way, then all the difficulties that go along with being a scientist, they can have some motivation to actually go through all of that. All right, so yeah, as I said, art and solar electrodynamics, let's extend OM and V, make these same type of things, reveal them at the conference as well. And then you've got that emotional connection that can be going on. And then I assume this is going to work really well. Our first summer school went really great. If this type of mini, CubeSat solar observatory thing was funded as part of the 2020-24 Heliophysics conference, I think it would go over really well too. We need to capitalize on that. Suppose we distributed a bunch of ground stations to schools across the country, particularly in the Midwest. As storms go through, right, we already have the notion that as these big storms go through, major convective actions impact on the ionosphere, right, we end up seeing those, or should see that in the ionosphere. If we have a high density ground station network across the country, and then we launch one or more CubeSats with, say, an RF beacon on there, so lower altitude, maybe even a Faraday cup on the front just to get density at the local altitude. As those CubeSats went over with the RF beacon, you got the two different frequencies, measure the phase difference by the ground stations. We can actually construct, the densities of what's going on in the ionosphere, and we might actually be able to see some of these things. So this would be a longer multi-year effort, but then it also provides a longer multi-year outreach, not just emotional with the art and other things like that, but then you can form connections like, a person's in a place, a massive storm comes by. Say you're in middle school or high school, big storm comes by, and then the next day maybe you can actually see the results of that in the ionosphere using the equipment that was actually at your school. It provides hooks that students can connect to, and if all the software is open source and available, the whole stack is there. They can go in and produce their own visualizations or tweak it or whatever. So this could be a very long-term thing. Twitter changes what you see, but I clicked on one of these storm things not too long ago because I thought it was a cool picture. Now I'm seeing it all the time, but it just reveals there are people out there that are interested in big storms going by, seeing the pictures and all that. And if we had a process that actually mapped the ionospheric impact for every single Twitter picture of a storm, you could have a thing, here's what happened to the ionosphere. So all open source and things like that. And then, you could go to more data sources. You could have all sky cameras. You can have magnetometers. If you really want to spend, put money into it, you could install all kinds of radars everywhere. I mean, that'd be great. But it just becomes a program, and each year or every other year as part of the summer school, we can extend to a different data source, and that ensures that all those different data sources and structures in different areas of the community are all adequately represented in the open source science software stack. And then, if you have just knowing that you're going to go have to present in front of a bunch of people, provides its own impetus to actually get stuff done. Of course, this would have to be fun, because they require groups across PyHC and then, hardware and time and all that stuff. But it's possible, and I think it could have a really transformative effect in some ways on NASA's interactions with the public. All right, so thank you. I'd hoped to be able to do a Licator demo. I'm already over on time, but there's a technical issue, so I couldn't get my mics hooked up in a way that you could hear. But I am hoping in the future to be releasing more songs, or maybe even a cover album where it'd be like a before and after. I'm going to cover a song just as good as I can, and then after I record that and have that done as a song, I'll go back and I'm going to apply the Licator as an audio effect to all the sub instruments and vocals and things like that I'm going to do to show what the music sounds like after the Licator. So so it's science and art. So thank you for the time and the extra time to share this type of work, and I really appreciate it.
Great, thanks, Russ.
Open for questions.
I like all the ideas, and I love the idea of having increasing the emotional connection between citizen science and the scientists. That's a great idea. So if people want to, even though we're past time, if we can stick around for a few questions if people have them. While I wait for people to possibly chime in, I'll ask, is your mapping technique ready for use? Is this something we should contact you if we have a use, and you would work with us on field line mapping? Or?
Absolutely. Yeah, so the OMBV software is already out on GitHub, and it even has hooks on the outside for different magnetic field models and corresponding enneagram routine. So so the technique can be applied as is to alternate magnetic fields. I have found, at least on the Earth, because of the huge change in field line length, that I have not found a single set of settings that now works at the equator and at the poles. At some point, kind of have to switch. So I think there could be more work to make that more automatic and seamless, but even without that, I think my technique would work in at least, multi-run.
Okay. Any questions? Understandably, people are having to run at this point, but I'll ask one more question. What do you have any future aperture related projects in mind? Maybe something beyond the Earth and the Sun?
Yeah, I was actually recommended that I take a look at like Jupiter or Saturn yet, because I've actually submitted on the Earth, and I ran into some resistance from, some pre-existing explanations. So I'm thinking about actually applying it to, yeah, other planets that have measurements of wave nature, of, the transfer of power at the poles. So,
Okay, fantastic. We have a couple people chiming in saying great talk, very interesting.
thank you.
So, well, why don't we end it there so people can go about their day. So, once again, thanks, Russell. That was a fantastic talk. Glad to have you.
Thank you so much. I really appreciate it.
All right, take care.
Cheers.